You know, in chemistry, you sometimes run into equations that just look impossible, right? A complete jumble of symbols and numbers that seems to have no logic at all. But what if I told you there's a hidden code, a secret language that can turn all that chaos into perfect order? Well, today we're going to crack that code. Okay, take a look at this beast. At first glance, balancing this thing seems like an absolute nightmare. I mean, where would you even start? You could try to just guess the numbers, but you'd probably be here all day. It feels impossible. But it's not. There's an incredibly systematic, kind of beautiful way to solve it. And the secret, the thing that unlocks this whole puzzle, is a hidden code that chemists use. It's a special value assigned to each and every atom called the oxidation number. Think of it as the master key that reveals the hidden logic behind the whole reaction.
So what exactly is it? Honestly, the best way to think of an oxidation number is like an accountant's ledger, but for electrons. It's just a number we assign to an atom that helps us keep track of whether it has, technically lost or gained electrons in a compound. And this one simple accounting trick is what makes balancing these crazy equations totally possible.
And this isn't just some abstract theory for a textbook. It has really powerful practical uses. See this block of magnesium on the hull of a ship? As a pure element, its oxidation number is 0. But it's put there on purpose to rust or, oxidize instead of the steel. When it does that, its oxidation number changes to +2. It literally sacrifices itself to protect the entire steel hull from corroding. It's a perfect real-world example of this hidden logic at work.
So here's the most crucial point, the main idea for this whole thing. When an atom's oxidation number goes up, we call that oxidation. And when it goes down, we call that reduction. And here's the rule. In every single one of these reactions, the total increase from oxidation has to perfectly balance the total decrease from reduction. That's our guiding principle. That's the whole game.
Okay, so to use this powerful key, we first need to know how to make it. That just means learning a few simple rules for assigning these numbers. And once you've got them down, you can unlock pretty much any equation you come across. And here they are, the 4 foundational rules. Rule number 1. An element all by itself, like a piece of zinc metal or oxygen gas floating around, its oxidation number is always 0. Easy. Rule 2. A simple ion, like a chloride ion with a -1 charge. Its number is just its charge, so -1. Rule 3. In a neutral compound, all the oxidation numbers have to add up to 0. And finally, Rule 4. For a more complex ion, they all have to add up to the ion's total charge. That's it. And to make things even easier, some elements are incredibly reliable. You can think of these as your fixed starting points, your anchors. Group 1 metals, they're always +1. Group 2 metals, always +2. Fluorine is always a -1. And oxygen and hydrogen are almost always -2 and +1. We use these known values to figure out the tricky ones. So let's try it out real quick. Take sulfur dioxide, SO2. All right, we know each oxygen is usually a -2. We've got 2 of them, so that's a total of -4. Now, the whole molecule is neutral, so all the numbers have to add up to 0. So what plus a -4 equals 0? Yep, +4. That means sulfur's oxidation number here has to be +4. Simple as that. Let's do one more, this time for an ion, the nitrate ion, NO3 with a -1 charge. We've got 3 oxygens, each is a -2, so that gives us a grand total of -6. But wait, the whole ion has a charge of -1, so the oxidation numbers have to add up to -1 this time. What number plus a -6 gives you -1? +5. So the nitrogen atom here must be a +5. See? It's not a guessing game at all. It's just a little logic puzzle. All right, we have forged the key. We understand the rules. Now, let's go back to that monster equation from the beginning and use what we know to unlock it, step by step. Let's do this. Okay, step 1. We assign oxidation numbers to everything in the equation and find out what's actually changing. Over on the left, in the permanganate ion, manganese is a +7, but on the product side, it's just a +2. That's a decrease of 5, so it's been reduced. Meanwhile, our iron atom goes from +2 to +3. That's an increase of 1, so it's been oxidized. And step 2, this is the magic moment. This is where it all clicks. Remember, the total increase has to equal the total decrease. We have a decrease of 5 for the manganese, but only an increase of 1 for the iron. So how do we make those balance? Well, we need 5 iron atoms for every 1 manganese, right? 5 times that +1 increase gives us a total increase of +5, which perfectly balances out that decrease of 5. And just like that, we know the ratio of our main ingredients. We just have to put a 5 in front of both of the iron ions. And believe it or not, the hardest part of this puzzle is already solved.
Okay, next up, we have to balance the electrical charge on both sides. On the left side, the reactant side, we have 1 minus 1 ion and 5 plus 2 ions. That gives us a total charge of plus 9. On the right side, we've got 1 plus 2 ion and 5 plus 3 ions, which adds up to plus 17. So, to make the plus 9 on the left equal the plus 17 on the right, we need to add 8 positive charges. And that's exactly where those H plus ions come in. We need 8 of them.
And now, for the final step, we just tidy up by balancing the atoms. We just added 8 hydrogen atoms on the left, so to balance that out, we need 8 hydrogens on the right. And since water, H2O, has 2 hydrogens each, we're going to need 4 water molecules. And here's the cool part. If you go back and check the oxygens, you'll see they magically balance themselves. 4 on the left and 4 on the right. Perfect.
And there it is. The puzzle is solved. What looked completely impossible at the start is now perfectly balanced. And we didn't have to guess a single thing. We just applied the rules of chemistry's hidden code.
So why does all this matter? I mean, is it just a clever trick for chemists? No, not at all. This method actually reveals something really fundamental about how chemical reactions work. At their core, they are all about the movement of electrons.
So here's what you should remember. Oxidation numbers, they're just a system for tracking the flow of electrons. That's it. And balancing a big, complex equation is really all about balancing that flow, making sure the electrons lost in oxidation are equal to the electrons gained in reduction. This method isn't just a trick. It's like a window into the beautiful, hidden order that governs the entire chemical world.
And it really makes you wonder, doesn't it? By learning to see this completely invisible accounting system for electrons, we uncovered a deep rule that governs how the material world works. So, what other invisible rules are out there, just waiting for us to decipher them, that bring order to the amazing world all around us?